Hello everyone. So previously you learned about discrete and continuous random variables. Now we would like to see how about the distribution, how we can actually find a distribution of those random variables. So we will try to see based on the experiment what would be the distribution because there are depending on the variables, random variable or continuous variable, depending on the experiment, depending on the behavior of those observations, then we have to identify what would be the distribution of those random variables. At first, let's talk about uniform distribution. By the name of it, you can maybe you can guess that maybe the probability for each of those possible outcomes would be the same. So let's give you an example, the uniform discrete random variable. So over there, so let's say we have the uniform distribution. So we are talking about the uniform discrete distribution. So let's say we are rolling a die and then it has 6 sides. The possibility of each of those outcomes, that means if I throw this die, and the possibility of each of them would be the same. That means it actually follows uniform distribution. You can see the functional form. It says that the function of that experiment would follow uniform discrete distribution, and then let's say the outcome could be 1, and the probability of the outcome would be 1 over how many outcomes can be there. K is the total number of possibilities. So possibility is 6 of them. Since it's 6-sided, it could be any of them. So if the possibility of getting 1, if we throw once, then you will see that possibility would be 0.167. And then same thing for all of them. And then we don't have any more outcome in here. So we only have 6 outcomes. Okay, so let's talk about the binomial distribution. So in binomial distribution, the experiments we have, we would think about we are repeatedly doing the trials, throwing the coins a few times. That's a repeated trial, right? And then each trial should have 2 possible outcomes. We cannot have more than 2. Success, failure, let's say a tree is dying or a tree is live. And then the probability that a particular outcome will occur in a given trial, that means let's say the probability of a success, probability of a failure, or probability of each of those possibilities should have some probability right in there. So each of those probability that should be the same from trial to trial. It might be easier for you if I give you an example. So we said that in an experiment we can have n repeated trials, throwing the coins let's say a few times, and then each trial has 2 or more possibilities, and then we have to define what we are calling as a success. Throwing a coin, getting head or getting tail, which one is your success? So you have to define that. If someone defines getting a head is a success, or someone defines getting tail is a success, then the distribution will change. And then when we are throwing the coins, let's say when I'm throwing coin once and then throwing coins again, each of those is a trial in that experiment, and then one is not affecting the other. It's a discrete random variable, and then the distribution of that discrete random variable follows this function. Let me read this function for you. So in this function, we have how many times we've thrown the coin, or how many trials we have, and then each of those, let's say we've thrown a coin 5 times, and then let's say getting head is our success. So we can get 0 head, we can get 1 head, 2 head, and then up to how many times we actually thrown. is the probability of success. So like we said that from trial to trial, the probability of getting the head or tail would be the same. That means trial to trial, the probability we are getting is the same. So that's the probability, and then x is, it could be getting 0 times getting head, once getting head, or 2 getting heads. The opposite is that the failure, and then we can say that failure could be, we can define it by q, and then we say that 1 minus p is the probability of failure. Let me show you using an example that might be easier for you to understand. So the binomial distribution, the discrete distribution we have, I actually took the function from there, and then over here the first one is the n choose x. That means the total number of times you actually thrown, and then total number of possibilities of the success, you can say that, and then each of those we can define by x is the random variable. So combination, that's a combination that we actually found before. N choose x, you can use that. So we say that number of success could be 0 up to n, and then probability of success, then probability of failure. If you add them to p plus q should be 1. And then let's say number of trial is n, and in an example we can say that we are tossing a coin 3 times, success is getting ahead, and the opposite, that means if we get tail, it would be the failure. So total number of times we are throwing them is the n is 3 times. So let's say we could have, in those 3 times, we could have 0 number of head, we could have 1, or we could have 2, we could have 3. That means in all of those, whenever we are throwing them, all of those could be heads. So that's the possibilities. That's the numbers we get for the random variable. How about the probability? How can we calculate the probability? So using this function, we can find the probability. So at first you have to think about, was the n choose x, that means the number of trial is always 3 choose, 0 is the x value, because this is the let's say getting the heads, we did not get any head in any of those tosses, in those 3 tosses. So we can say that 3 choose 0, and then multiplied by each of those possibilities. So the getting head or tail, each of those should be 0.5. The possibility is 0.5 because this is an unbiased coin. So you know that since we have unbiased coin, each of those cases the probability would be 0.5. But then again, since we don't have any heads, so x is 0 in this case, and then the q is the 0.5 again, and then n is the 3 minus 0. So that's how I got this probability. Let's say the probability of getting 2 heads, that means 3 choose 2, and then 0.5 power 2, and then 0.5 power 3 minus 2. That's how I calculated them. If you sum them, all these probabilities, then you will see that they are exactly 1. And then in the binomial distribution, we can easily find the mean and the variance of the distribution. So you can see that if we need to find the mean and variance, what we need to do is that we need to multiply what's the probability of success, and then in the trial, how many trials, how many times, let's say we repeated that. And then if you multiply by the probability of failure as well, then you would get the variance. If you go to the table in the appendix of the textbook, or you can use any online probability calculator for the table, if you look at the table 8.1, or maybe you have different number in your textbook, so you can use other tables as well. So you can see how many trials we have. The example I showed you, that we have three times we toss the coin, and then each of those cases, the possibilities where the probability of getting a success was 0.5. so you can see that we are actually in here. So if you use these probabilities, probability of getting 0 head, probability of getting head twice, probability of getting head 3 times, so all these probabilities you can find that. But in Excel I actually showed you by 2 decimals, 3.8. That's fine. And then you need to match in the table that how many trials you have, and then what's the probability value, and then what's the each of those number of successes you have. The next one is the multinomial distribution. So you can see that in the multinomial distribution, it has most of the properties we have in the binomial distribution. You can say that this is a generalization of binomial distribution. So the properties we have in the binomial distribution, we will consider all of them, except each trial could have more than 2 outcomes. Then we call them a multinomial distribution. So you can see that the distribution has everything that the functional form is similar to binomial distribution, only we have more than 2 outcomes. And then you can see that if we have more than 2 outcomes, the probabilities and the random number of trials, all of them we generalize them. Number of trials is same, but the outcomes, you can see that we generalize up to k, and then possibilities are changing. For example, you can see, take a look at the example we have in the textbook. As I always say, that maybe the page number or the example number may not be the same in your textbook, but you can find the multinomial distribution example. So for example, you can see that we have a deck of cards. In the deck of cards, we are thinking that we are actually getting 5 cards from there, and then we have 5 trials, and then I would say that I would like to get maybe 1 spade, 1 heart, and 1 diamond, and then maybe few clubs, or let's say 1 club. And then for each of them, one of the trial is not affecting the other trial. That means when I am actually picking the cards from there, and then for each of those cards, the possibility of getting those have the same probability, and then each of those probability we can plug in here. So number of trials would be 5, and then for each of them, since I am talking about 5 of them, 4 of them, and then 1 spade, 1 heart, and then 1 diamond, 1 club. And then since we are taking them once, and then we can say that if I want to find the probability of them, and then trying to find them in the multinomial distribution, because the outcomes is not 2. It's not just the getting, let's say, getting one of the card, let's say maybe heart or spade. It's not like that. We can have 4 of them. That means it's not the outcome is not 2, it's more than 2. That's why it's multinomial distribution. Then you can identify for each of those what is the probability and how many we can get for each of them, and then you can find the distribution of multinomial distribution. Let's talk about hypergeometric distribution. It's similar to binomial distribution, but then again there is a difference. So let's say in binomial distribution, the trials were independent, but in here the trials are not independent. So if we have 2 outcomes and we select the objects from without replacement, so that means the first I got the outcome from a trial, and then I actually separated them, then I do the second trial and then get the outcome. So that means they are actually dependent, and then every time previously the probability in the binomial distribution was same, but in here the probability will be changing because it's without replacement. The situation changes every time. So you can see that since it's changing, that means we need to add more parameters in our distribution. So let's say we have an experiment, and then in total in that experiment, let's say we have a population. What's the population size? In that population, the success we have, we need to define them. What we are calling them a success. And then the rest of them will be the failure. Is similar to the binomial distribution. We have success, we have failure. But in each of those trials, the probability is changing. The probability of success initially is k by n, because we have k number of success, and then the total number of population size is capital N. The next time when we actually try to get the outcome, the next trial, since we are not using the previous one, since it's without replacement, then we have one less in both cases, the population size and the outcome we have, the success we have. So that's why in the hypergeometric distribution, you will see that we have the population size, we have the next time we have the sample size, and then in the population, how many were success we had. And you can see, we can find the mean and variance from there. Let me give you an example that might be easier for you. We have lots of examples in the textbook. So you can see that I actually tried to add the function of the hypergeometric distribution. This is again a discrete distribution. So in this discrete distribution, so let's say in a pond, we release 20 fishes. I'm not saying what kind of fish, maybe same kind of fish or different kinds of fishes. Before releasing them, I tagged 5 of them. That means from the 20 population size, we have 5 successes. So I said that whenever we will have the tagged fish, that's a success. So that means we have 5 successes from 20 sample size, population size. Then what we did, next time we go to the pond and we caught 4 fishes from there. And then in those 4 fishes, we said that we could have 0 tagged, 1 tagged, 2 tagged, 3 tagged, or 4 tagged fishes, right? So that means we have the outcomes could be no tagged fish, all of them tagged fish, or 0, 1, 2, 3 up to 4. So I identified them. So using this function, we can calculate, just like I showed you before, how I calculate the binomial distribution. You can just plug in all these values and then find what might be the probabilities. Let me show you one of them, and you can do that. Also, you will see that there are lots of online calculator. I'll show you one of them, and you can find whatever you feel like comfortable doing that, just to match your values. But in the exam, you cannot use those online calculator. You have to use your own calculator. So at first I tried to see that how many were tagged. 4 of them were tagged, and then 5 of them were tagged in the population, and then I'm selecting only, I'm saying that there will be 0 of them will be tagged whenever we actually caught them in the second time. So in the 5 choose 0 is 1, and then I say the next one is the n minus k, choose n minus x. So I try to see that n minus k is the 20 minus 5, and then choose n minus x is the 4 minus 0. So the combination would be 1365, and then I say that what is the total combination if we have those possibilities. Then the population size 20 choose 4 is this number. Then the probability would be 1 multiplied by 1365 divided by 4845. That's how I got this number. So I did the same in a So you can see that I did the same in Star Trek. This is the website. I try to see if they have any calculator. If you type in Google that hypergeometric distribution calculator, you will find many of them. And then I just plugged in population size and the number of success and then sample size. Same thing I did in here. And then you can see that the number of success is 0. Then you will see that the number is 2817. If we say less than 0, if we say less than or equal 0, and then each of those probabilities, let's say more than 0 would be the rest of the probability. Maybe I will give you in the assignments or in the exam, let's say we have these possibilities, and then what's the probability of getting 4 or more than 3? More than 3 is 4. More than 2 is 3 and 4. You have to add all those probabilities. Similarly, we can, just like what we did before, we can generalize them. So we can say that we have more, and then we can actually generalize into the hypergeometric distribution. And then when we generalize them, that means we have partitioned them, the outcomes we have, the numbers of successes we are getting, we can partition all of them. And then you can see that we would have the multivariate hypergeometric distribution. So you can see partitions are happening in the outcome, and the partitions are happening whenever we have how many successes we have. That means we can have elements of successes, and then but the total number of population size and total number of samples, this is same. Okay, so next we will be talking about the negative binomial distribution. So all I'm trying to do is that giving you an idea in what situation and how we can actually say this is the distribution that we need to follow. So I already talked about binomial distribution, and then the uniform binomial, and then multinomial distribution, hypergeometric distribution. So you have to be able to identify, if I give you a situation, you should be able to identify what kind of distribution I have to use, and then you have to identify the parameters, and then you can find the probabilities, just like I'm showing you in the Excel file. So let's talk about the negative binomial distribution. So the negative binomial distribution, it actually satisfies all the properties we have in the binomial distribution. You saw that before, binomial in the discrete distribution. So we are repeating the trial until, that's the difference we have, until we get a fixed number of success. Let's say I throw a coin, and then until I get 5 heads, I will continue the trials, continue my experiment. Then you will see that it's actually following negative binomial distribution. The parameters are similar, only difference is that when we get the, or since we are talking about getting the fixed number of success, so that means when we are going to get that. So you can see we have the functions, and then similarly we have the outcomes, and then we have the when we are producing the number of successes, and then the probabilities that we have in those trials. So if I say in an example, maybe in an exercise, if I say that I'm interested to get that many number of success, or I'm interested to get that many number of item, then you will see that this is actually negative binomial, and you can easily plug in them. Similarly, in the geometric distribution, you will see that it's similar to negative binomial, but only thing you have to consider is that when we have first success, previously we said that a fixed number of success, if we are only considering when we get first success, let's say I throw a coin, and then when I will get first time tail, that's when I'm going to stop. That means that's my first success. then you can see that the form is similar to what we had in the binomial distribution. Only difference is that we are not using the n choose x, and then p power x is not there. Only we have p, q, and x power 1. That means probability of success, probability of failure, and then all the properties we had. Everything will be same in the binomial distribution. Only difference is this part, the first success. Let's talk about Poisson distribution. Poisson distribution is easier to identify than other distributions that I talked today. So let's say the Poisson distribution, we can say that the distribution, since we are talking about all the discrete distribution, the random variable is a discrete random variable, and that measures the probability of a given number of events happening in a specified time period. So you can see that we mentioned that it could be time interval, could be a length, could be any length. It could be a minute, day, or year. For example, in a given in a street, in a year, the accidents are happening in that road. The possibilities are really low, but the given time is large. So you can think about each outcome. That means the number of accidents or accidents happening in a given road in a year is happening independently, and then we can have the outcome. We can also say that not in a year, or it could be a short time, or it could be in a day. So let's say in front of my house, how many accidents that could happen in a day. So then we have to think about the possibility is really low, but we can identify what might be the possibility. The probability itself, we need to know on an average how many accidents are happening. Then in a given day, 0 accident or 1 accident, 2 accidents, 3 accidents, then we can find them, right? So you can see that the distribution, we have only one parameter. The parameter is that what's the average. That means on an average, what is happening. If we are talking about accidents, then on an average, how many what's the possibility or the probability of accident in that road. And then the 0 accident, 1 accident, 2 accident, and there could be many number of accidents. 0 accident is probability would be higher, a number of accidents more than 1, more than 2, or let's say equal to 2. We can all find them using this functional form if we only know the mean of them. In the Poisson distribution, the interesting thing is that mean and variance both are exactly the same. You will see that we gave you some examples in the textbook, but the other examples could be let's say number of deaths occurring whenever people, let's say, riding a horse, or maybe people are dying from a rare disease. Let's say dying from a rare disease in a month in a city. That means the occurrence is really low, and then we have the timeline. You will see that there is a generalization, or there is a conversion, or there is a whenever we have the sample size is really large, but the probability is approaches to 0. That means really low. Sample size large, probability is really low. Then the Poisson distribution, Poisson distribution and binomial distribution, we can say that the binomial distribution approaches to Poisson. So if you think about the failure and success, then again, if we have a success, let's say the examples we had, the success probability of success is really low, but the sample size is large, then we can say that the binomial distribution approaches to Poisson distribution. So next we'll be talking about the continuous probability distribution. Okay, so next you will see the continuous probability distribution. The last thing I would like to say to you all is that maybe I will ask you for any given distribution I talked today, the discrete probability distribution. Maybe I will ask you to find the specific value, probability of getting more than some value. Then you have to consider which value I'm talking about, and then what are the values included in there. Or I might ask you to probability find less than some value, less than 3 maybe. Probability of finding exactly one value. Probability of finding less than or equal, that means I'm including the value and then less than value. That means you have to think about the finding the probability distribution, the distribution we have in here, and then in the objective what I am actually asking you to find the probabilities, which probabilities I have to add them. So if I talk about getting only 4, that means this is the probability. Getting less than 4, you have to add all these 3 probabilities. Same thing for binomial, same thing for hypergeometric and other distributions that I showed you today. So you have to think about what is the question is asking, what is the objective, and then find the distribution just like the way I showed you. After you have the distribution in a table, then you can easily find the objective probabilities. So the discrete distribution, we can see that each of those values is up to random variable values. We can find the probability. Thank you.